Welcome to Unlocking Materials in Omniverse. In this talk, we will tour materials in Omniverse and USD. We'll review MDL and its approach to modeling physically accurate materials, and we'll look at new features in MDL 1.7. In Omniverse, we'll review the core materials included with applications, and discuss the library of preset materials available for use in production. We'll take a look at our new material graph editor for authoring bespoke materials, and we'll look at the various approaches to material conversion between shading systems.
At the heart of the Omniverse material system is our material definition language, and I want to spend some moments explaining you what it is, how it works, and how you can use it also outside of an NVIDIA Omniverse. The material definition language is a technology that we developed at NVIDIA to define physically based materials for our physically based rendering solutions. So what are we talking about when we talk about physically based materials? Let me give you some examples. So of course, this is everything that you need to build your objects. So we are covering things like glass or the car paint for this car or the metals or the rubber for the tire. There might be advanced effects in the car paints. In this case, we have flakes in there. A product designer might need leather or fabrics, like you can see for those watches here. And an architect needs things like the wall paint, the wall materials itself, and all the things that his furniture is made of. Those virtual statues here use glass and transparent effects as well as translucent jade-like materials. And here we have an example of human skin, which uses subsurface scattering as well as the hair with the special hair light interaction. The material definition should be rich enough so that you can simulate the light transport inside of a glass to a high degree of accuracy, generating caustics and other effects, like here, those dispersion effects for this gemstone. And the goal here is not to just define the materials, but define them in a way so that we can match the appearance of a single material with different rendering techniques, because at NVIDIA we develop new renderers all the time. So for sharing the scene across the renderers, there are technologies available. Omniverse uses USD as a shared scene database, but we also want to share the materials across the different renderers so that if you switch between renderers, you can have a consistent look depending on the capabilities of the renderer. So here an example what we can achieve using this. On the right side, you see a simple OpenGL rasterizer. In the middle, you see an interactive and fast ray tracer. And on the left side, you see a high quality light simulation path tracer. And they all use the same scene and the same materials. And the rendering is not exactly the same because the different rendering algorithms don't cover light transport simulation to the same degree. So there are small differences, but in all cases, the material is perfectly recognizable. So how did we achieve this? We took a look at traditional shading languages and analyzed what they are used for. And we identified 3 areas. First, there's texturing, which means the variation of the material across the surface. You might use bitmap textures and texture lookups to do this. You might define procedural texturing. You might transform the bitmap on the object using UV transforms or project it onto an object. This is all what we define as texturing. Then you have what we call definition of the material itself. This covers basically the definition of how the light interacts with the surface. The surface might be translucent, it might be transparent, it might reflect glossy, or you might have sheen effects, or it might even emit light itself. And this is all portable, but there's one part that is typically also implemented using the same shading language that's not portable, and that is the evaluation of the actual material, so the material implementation. So if you have something like a glossy reflection, you might basically do something like an environment lookup, or you might trace n-rays depending on what kind of renderer you have. Similar shadows, you might use shadow maps or ray trace shadows. And for transparency, you might sort polygons, or you might need use ray continuation to evaluate that. This is not portable. So in MDL, we basically said we define the part that is portable, and we have a procedural programming language that you can use for texturing with full programmability. And we have a declarative system for the definition of the light object interaction, which covers all the effects. And we leave it to the renderer to actually implement this. So the renderer, depending on its architecture, might evaluate the material model using different techniques. To drive this home, MDL is not a shading language. It defines what to compute, not how to compute it. And it has no programmable shading. You can't access illumination direct. There are no trace calls and no sampling. So how did we make this as flexible as traditional shading languages? This is by defining a material model that all materials are based on, and that covers things like the surface shading, the shading inside the volume, and actually some geometry manipulation that you typically do in materials. And to define things like the emission, the surface, and the volume, you use combinations of distribution functions, BSDF, EDF, and VDF, and combine them in a very flexible manner. And next we want to take a look at what this actually looks like combining those. So what do all those different BSDFs that MDL defines look like, and what can you do with them? I will explain this using Adobe Substance Designer, which has full access to all of the components of MDL, and you can create materials out of them. On the right, you see the material struct that we talked about just before, and the material surface substruct. And now we have here a selection of some of the BSDFs that you can use to create your materials. We have a diffuse reflection, which you can use to create the basic powdery surface. We have diffuse transmission, so this is good for things like leaves or paper. We have specular interaction, basically mirror-like reflection, as well as perfect glass. We have a whole zoo of microfacet models. I don't want to show all of them. I just want to show the most important one, which is probably the GGX, which you can use to define glossy surface behavior. Again, also for reflection as well as transmission. So you get your basic frosted glass. We have a very special BSDF in the form of the measured BSDF, which can use measured material data. In this case, this is a measured green car paint that's directly rendered using this BSDF. Then we have various backscattering behaviors. We have essentially retroreflective paint using the backscattering glossy or velvet-like sheen effects. So that all are the elemental distribution functions on the surface. We have also various EDFs for emission. You can have your basic uniform emission, or you can have a shaped emission in the form of a spot EDF, which emits mostly into your direction here, or an IS light profile defined measured EDF. On the volume side, we have a single anisotropic phase function. This is the Henier-Greenstein phase function, which you can use to define subsurface scattering materials. And the individual BSDFs themselves are probably not suitable for a lot of materials. Most of the time, you want to first modify them and later combine them to create more complex BSDFs. The simplest modification is just adding color to it. You can do this either uniformly or based on a Schlick term, making a color change based on direction. Or if you want to have a more detailed color change, you can use the measured curve factor. And in addition, we have a physically based thin film interference effect, which will also add color to your BSDF. Once you have colored them, you can start combining them. There are basically, again, a whole zoo of combiners. I will just show two examples. First is this weighted layer, which basically mixes two BSDF together. In this case, it's twice a GGX, but one is more bluish and one is more yellow. And the yellow creates a sharper highlight versus the bluish, which creates a more rough glossy behavior. So with this, you can create more complex highlight behavior. Then, of course, we have directional dependent layering operators. The most important one is probably the Fresnel layer, which does a directional dependent combination of two BSDFs using the IOR. With this, you can, for example, combine a specular BSDF with a diffuse reflection to create what is essentially a dielectric. You can do this recursively. So in the end, the graph can become quite complex. Most of the time, artists do not want to go into so much detail for every material that they create. In order to make the life of artists easier, we actually created a number of high-level components that allow way quicker generation of the common materials that people encounter. We currently released the MDL version 1.7 just at GTC. This has several additions. One is, for example, a new sheen modifier that you can put on top of any other BSDF. This allows very nice fabric materials, for example. We greatly improved support for volumes. So we have now support for OpenVDB as a 3D texture. We added a tint modifier for volumes, and volumes can now emit light. And there's a whole list of other smaller additions and improvements, an unbound mixer that is very valuable when you want to convert material X content. We allow volume mixing. We allow texturing of mixer weights for EDFs. We have a shaping modifier for emission that allows undercoat emission, and many more smaller additions. So we already saw that with MDL you can define a material for multiple renderers, but this is not the only benefit that you get with MDL. MDL also works very well with measured workflows. We saw the measured isotropic BSDF already, but it also works very well with spatial varying BRDF models from scanners. So you can easily also convert AXF from Xsite to MDL. It's from the ground up designed for parallelism. So we have little data dependency in MDL. All our functions are side effect free. So MDL content, of course, runs very well on highly parallel machines. And then we have a system of modules and packages, as well as MDL archives, which you can use to build and ship whole catalogs of materials. So it's very good for organizing your content. If you want to integrate MDL into your renderer, we have an MDL SDK available. This is the same API that's used for adding MDL to our Omniverse renderers, RTX real-time and RTX path trace. It's available with MDL 1.7 support, and it features a database for material definitions where you have a DAG view on your materials with several compilation modes, and you can do parameter editing. And then for various renderers generate code. We have a PTX backend. We can output LLVM IR, so you can do whatever you want with it. We have a native x86 backend as well as an ARM backend by now. We have HLSL code generation as well as GLSL. And for very low-end targets, we have texture baking mechanisms as well as a feature called distiller. The SDK comes with many code examples, and there's of course lots of documentation and tutorials. Since 2018, we also have an open source release under the very permissive BSD3 clause license. It's the full SDK with an additional API not featured in the binary version, the core API for lower level access to the compiler. And right now it doesn't feature distilling or GLSL backend, but we are working on this. MDL works very well with RTX, so we in particular have two examples that we ship with the SDK, one in the form of a Microsoft DXR ray tracer. It's an example path tracer with GLTF support and uses the same HLSL backend that NVIDIA Omniverse uses. And then we have an optics ray tracer that uses the PTX backend and works both with OptiX 6 and OptiX 7. So integrating MDL in an RTX-based renderer is simple. It's also simple for many other targets. We also ship an example integration into Autodesk Arnold, for example, that is also available with the SDK. And for fixed material models and ultra-fast rendering, we have distilling. This is an automatic lossy reduction of any complex material for fixed material models. Here we see an example that we also ship with the MDL SDK, which simplifies any MDL content to be rendered in Unity. So much for the technology MDL, and with this I give back to Frankie to talk more about the material support in NVIDIA Omniverse. Thank you.
In a previous section, Jan reviewed the low-level MDL components that serve as the foundation for constructing physically based materials. To help manage these low-level components, Omniverse applications ship with a set of core materials that use these components to broadly model a large range of appearances. In this video, you're seeing an overview of each core material and their parameters. Parameters for core materials have default values, which need to be set in order to create a specific material appearance. OmniPBR is the primary material model used throughout Omniverse. It is designed to be flexible, providing metallic and dielectric appearance modeling, along with emission, opacity, and normal mapping controls. OmniPBR is the foundation for many materials in Omniverse, and provides both real-time and path trace simulation. Here we see texture maps being used to create a multi-layered metallic and painted material. OmniPBR Clearcoat builds on OmniPBR, adding a second Clearcoat glossy lobe to the material. This material is commonly used for multi-layered materials such as car paints, polished or lacquered floors, glazed ceramics. For performance-sensitive content, it's best to use the material that most closely matches your material needs. For transmissive materials, OmniGlass supports volumetric and specular transmission. Glass color and roughness are used to control the specular transmission, while absorption scale controls the absorption within the medium. Inspired by Autodesk's white paper on standard surface, OmniSurface adopts a similar approach to layering and mixing BSDFs to physically model a wide range of materials. OmniSurface supports diffuse reflection and transmission, subsurface scattering, glossy specular reflection and transmission, emission, sheen, opacity, clearcoat. It is our most comprehensive material and can faithfully model materials such as plastics, concrete, water, car paint, skin, foliage, foam, wax, wood, velvet, and metals. OmniSurface Lite is a slimmer version of OmniSurface that still provides multi-lobe secondary clearcoat with anisotropic controls, emission, and opacity. Like OmniPBR, when in need of performant rendering, we recommend using the OmniSurface that best models your material needs. Omniverse comes with a library of preset materials that allow for rapid visualization. Preset materials are built from our core materials and come pre-configured with initial parameter values and texture maps to represent a wide range of physical materials. Preset materials can be found in two locations. In the Materials window, you will find our collection of materials based on OmniPBR and vMaterials, and also in the Create Materials context menu. There you will find our presets for OmniSurface, which parallel the presets for standard surface. In the Materials window, there are two collections of materials hosted for you through AWS. Our base collection uses OmniPBR as its material model and is designed to function in both real-time and path-traced rendering modes. vMaterials is NVIDIA's curated collection of high-quality physical materials. The new vMaterials 2.0 has been fully integrated with Create and contains features such as high-resolution textures and infinite tiling. Material collections can be extended to manage your own library materials. In addition to our core and preset materials, Omniverse supports the import and creation of custom MDLs. In this example, Jan is using Substance Designer to create a shiny satin fabric material. Starting with one of Substance's high-level material nodes, he uses a physical metallic roughness material to simulate the anisotropic reflective threads. Cross threads are created by duplicating and blending the two materials together. Rotating the anisotropic direction and modifying the color of the second thread completes the look of the fabric. To load the material in Omniverse, you can export the MDL and configure your MDL search path to include any required material modules. You can then browse and load the material in Omniverse in the same manner as our native preset and core materials. In this next video, Jan will discuss using our material graph editor to directly author custom materials in Omniverse.
Most artists would want to work with higher level nodes that make material creation more efficient. And in Omniverse, we now have used the shade graph editor and expose materials through a set of such higher level nodes. So we have all kinds of materials that mimic real world material, metals, plastic, glass for thin walled and thick glass, as well as translucent material. And we also have a flexible material model, which is essentially a metallic roughness material model that should be familiar to most artists. And with that, I, of course, can do all the regular things. I can change color. I can make the material more dielectric or more metallic. And I can change roughness to get the effect of a rough metallic material. And with MDL, we can also create materials that modify other materials. So I'm not basically stuck with what I just created. I can now decide to add more stuff to this material. Like in this case, I want to add metallic flakes to that material that we just created. So we can see this here. Now I have the basic metal material that I created before, and I have yellow metallic flakes that I have put on top of this. And for full car paint, I of course would now want to do things like add a clear coat. We can also do this easily. So here we have apply clear coat material that again can take what we constructed before and then output this for final rendering. And we have a new material that is the blue base, metallic flakes, and clear coat on top. And I can do this recursively and add more stuff. Like, for example, I could add a simple sticker to this material. So this is the high-level set of building blocks on the material side. We see here already that we also have building blocks on the texturing side that simplify things. I will now show you this with a different scene. For texturing, Omniverse also comes with a number of predefined high-level texturing nodes with lots of controls that should make any texturing job easy. Of course, we have functions for bitmap texturing as well as normal mapping, and those come with a number of controls, so you can easily adjust the brightness of a texture or the placement of this texture on the object. And in addition to bitmap texturing, it's of course also easy to just do procedural texturing. So in this case, I will use now a Whirly noise procedural texture for the base color as well as the normal map. And again, those functions have lots of controls, so we can easily adjust the size of the noise function, as well as the shape of the cells. We have different shapes for cells, for example, for things like crystalline structures, as well as round organic shapes. And if you then want to combine multiple textures to create a new one, you can of course also do that. So in this case, I want to combine the whirling noise texture with the bitmap texture and use that to color my object. And I also want to use that to modify the reflectivity of the object. And at the moment, it's basically just showing the second texture because this is the Photoshop blend function. I can easily adjust the weight to just blend halfway between them. Or I have all the usual Photoshop blend functionality that you know and that you can use to then combine the two textures in different ways. And depending on what you choose, you can get quite some interesting effects quite easily.
The Omniverse ecosystem supports converting materials between many different material systems. This includes materials from Unreal, V-Ray, 3ds Max's physical material, Maya's standard surface, and soon Blender's principled BSDF. For many of our connectors, we provide the exported materials by mapping parameters from one shading system to another. The most common use of this is for export to OmniPBR. In this scene, we have some avocados with Max's physical material applied. On export, OmniPBR is applied to the objects, and the physical material's literal values and bound texture maps are mapped to their target inputs. This conversion works very well for material models that are similar. For more complex exported materials, we convert one-to-one shading functions to produce new MDL source. In this example, the connector analyzes the V-Ray graph and saves the newly generated MDL to our Nucleus project. You can find this level of conversion in our Unreal, Max, and Material X converters. The last form of conversion is the baking of BSDF inputs into texture maps. Here, the source renderer is used as a type of virtual material scanner. Each material is evaluated by the source renderer to output AOVs, which store the material's inputs. The AOVs are applied as texture maps to the object surface using a target material model such as OmniPBR. The virtual material scanner is currently available as a Max script that works on Max and VR scene files. In this example, the ship's materials are evaluated one by one to generate the baked textures and target materials. Once the baking and export is complete, the ship is loaded as USD in Omniverse Create. Thank you for joining us for our talk on materials in Omniverse. I'd like to thank my partner, Jan Jordan, for his contributions, and I'd like to thank the many beta users and early adopters for their continued feedback. For more information on OmniSurface, please check out our talk, Realistic Digital Human Renderings with Omniverse RTX Renderer. And lastly, we're excited to announce our inaugural NVIDIA Omniverse Users Group launching at SIGGRAPH 2021. Join us for a 1.5-hour action-packed session hosted by Omniverse senior leadership. Get a sneak peek into upcoming product releases, explore new resources, exchange best practices, celebrate each other's achievements, even win NVIDIA giveaways. Register today at nvidia.com/SIGGRAPH.